Alright, hello, this is Dr. Henry, and today we're going to be looking at the extent of reaction with equilibrium partial pressures. So the equilibrium constant K can be used to figure out what partial pressures are of reactants and products at equilibrium. So in the simplest type of problem like this, one equilibrium pressure can be calculated if you know what the equilibrium constant is and you know what the other partial pressures are. So let's look at an example of that. So nitrogen plus oxygen produces 2 moles of nitrous oxide or nitrogen monoxide. So for this reaction, here's the equilibrium constant. We know that the K is 1 times 10 to the negative 30 at 25 degrees Celsius. So if we knew that the equilibrium partial pressures for nitrogen is 0.78 atmospheres and for oxygen is 0.21 atmospheres, then basically we know what K is, we know what the pressure of nitrogen is, we know what the pressure of oxygen is, so we can plug those into this equation right here, and then the only unknown is going to be the pressure of the nitrogen monoxide. So if we plug those in, this is 1 times 10 to the negative 30. I've lost my arrow. There it is. This is the K. These pressures were given to us, so we're going to solve for the pressure of nitrogen monoxide. So we solve for that, and we get a pressure of 4 times 10 to the negative 16 atmospheres. I should have put atmospheres units on there for that. So that's the simplest type of problem. A more common type of problem uses the K to determine what the equilibrium pressures are of all the reactants and products at equilibrium. And this basically involves making what's called a Rice table. And Rice stands for the reaction, initial concentration or pressure, the change in concentration to reach equilibrium, and then what are the concentrations at equilibrium. So there are 4 steps to this. And it's important that you make these Rice tables because we're going to be using these a lot later. And so this is our introduction. I want you to use it like this to solve these problems. And we're going to look at 2 examples. One example that's not too bad, and then another example that isn't bad, but you have to use the quadratic equation to solve it. So for the reaction of carbon dioxide with hydrogen to make carbon monoxide and water, this is at 900 Kelvin. K is 0.64. And we know that the initial pressure, the starting pressure of carbon dioxide and hydrogen are 1 atmospheres. And for this, we're going to assume the starting pressures of carbon monoxide and water are 0. So let's make our Rice table. So the first thing we do is we have the reaction, and then we put our initial concentrations. So we know carbon dioxide is 1 atmosphere, hydrogen is 1 atmosphere, carbon monoxide is 0, and water is 0. So then, how much is this going to change to get to equilibrium? We don't know that, so we make that our X. So we know that water, since it's a product, it's going to increase by X. Carbon monoxide is going to increase by X. And then on the reactant side, because carbon dioxide and water are reacting, those concentrations are going to go down. So they're both going to get negative X's. So at equilibrium, carbon dioxide is going to be 1 minus X, hydrogen will be 1 minus X, carbon dioxide will be X, and water will be X. All right? That's our Rice table. And now we're going to use the values, these values at equilibrium. We're going to use to figure out what X is. So here's our reaction. Here's our equilibrium constant expression for this reaction. And we plug in what we know for each of those pressures. So carbon monoxide and water are X. Both CO2, carbon dioxide, and hydrogen are 1 minus X. We know K is 0.64, so basically 0.64 equals X squared over 1 minus X, and that's square. So to solve this, let's take the square root of both sides. The square root of 0.64 is 0.8. Square root of x squared is x. Square root of 1 minus x squared is 1 minus x. And then I'm just going to put that result right here at the top so it's a little easier to see. And then we need to solve this for x. So we end up with x equals 0.8 minus 0.8x. So 1.8x equals 0.8. So we solve that and we get x equals 0.044. And that's really, once again, that should be atmospheres, and I'm sorry for leaving out that unit. Once we know what x is, then we need to use x to solve for the equilibrium concentrations. So carbon dioxide and hydrogen were both 1 minus x, so that's 1 minus 0.044. So at equilibrium, they are 0.44 atmospheres. And I see a mistake right here. This should be point. Alright, so I made a mistake. If we go back one slide, this answer right here should be x should be 0.44, not 0.044. Sorry about that. So this slide is actually correct, although here, look at this. This should be 0.44. So this should be 0.56. So sorry, this should be 1 minus 0.44. So this should be 0.56 atmospheres. And this is correct. This should be 0.44 atmospheres. Oops. Sorry. Alright, and once again, so you use x in equilibrium concentrations to find the pressure. So this should be 0.44, not 0.044. So I screwed that up. Sorry about that. Alright, here's example number 2. So in this example, we have hydrogen reacting with fluorine to make 2 moles of hydrogen fluoride. So K for the reaction is 115, and it started with 1 atmosphere of hydrogen and 2 atmospheres of fluorine. Calculate the equilibrium pressures. So once again, we're going to make a rise table. So at the top we have our reaction. Hydrogen plus fluorine produces 2 hydrogen fluorides. So our initial concentrations are 1, 2, and 0. So then the change for hydrogen fluoride, it's going to be 2x, because x is the amount of hydrogen and fluorine that reacts, and since hydrogen fluoride has a coefficient of 2, its change is going to be plus 2x. Fluorine is going to be minus x, and hydrogen is going to be minus x. So at equilibrium, we will have 1 minus x for hydrogen, 2 minus x for fluorine, and 2x for hydrogen fluoride. So here's our equilibrium constant. And then we're going to plug in. So we have 2x squared over 1 minus x times 2 minus x. So that ends up being 115, because we know K is 115, equals 2x squared over 1 minus x times 2 minus x. And then if we start solving this, just divide both sides by 1 minus x times 2 minus x, and we get this. And then what we're going to do here is I'm going to go ahead and take 1 minus x times 2 minus x. So we have 1 times 2 is 2, 1 times x is minus x, plus negative x times 2, that's negative 2x, and then negative x times negative x is x squared. Alright, And so here's what we had here, and then so I just multiplied 1 minus x times 2 minus x. I get 115 times 2 minus x minus 2x plus x squared equals 4x squared. And then clean that up a little. I have 115 times 2 minus 3x plus x squared equals 4x squared. Multiply 115 times everything in parentheses, and you get 230 minus 345x plus 115x squared equals 4x squared. And then if I just move that last solution to the top here, what we end up with is subtract 4x squared from both sides. You get 111x squared minus 345x plus 230 equals 0. And guess what? That is a quadratic equation. So you can use the quadratic equation to solve for x. You've been waiting all these years for a reason to use the quadratic equation, and here it is. So if you use the quadratic equation to solve for x, you get 2.14 atmospheres or 0.968 atmospheres. And 2.14 is impossible because it would give negative initial pressures for hydrogen and fluorine. So x must be 0.968. And then you're going to use 0.968 and plug this back into these equilibrium concentrations to find out what the pressure of hydrogen is at equilibrium, fluorine at equilibrium, and hydrogen fluoride at equilibrium. And that's how you basically solve these problems. And most of these aren't quadratic equations. And there's a trick I'll show you in some later chapters how you can try to get out of using the quadratic equation. So look at the Google Classroom for your homework. Do the best on the problems. I'll be back tomorrow.